Welcome back. In this series of videos we're going to be looking at covalent and metallic bonding. Now in ionic bonding you looked at species that had either gained or lost electrons. But some elements, the energy required to do this is too high. So to be energetically favourable, it makes more sense to share electrons rather than donating or accepting electrons. That sharing of electrons is a covalent bond. So we're on page 2 of the notes and we're looking at these definitions of bonding. So a covalent bond is a shared pair of electrons, one from each donor atom. But covalent bonding, like ionic bonding, is an electrostatic attraction between a positive and a negative. In this case, it's the electrostatic attraction between the nuclei and the bonding pair of electrons. The other thing you need to be aware of is the bond length, and that is the distance between the two nuclei of the atoms that are covalently bonded together. And as with all bonding, their strength is determined by the size and the charge. So in this case, the shorter the bonds, the stronger the bonds. And the more bonds you have, again, the stronger the bonding is going to be. And we can see that in the example at the bottom of the page, that the iodine-iodine bond is longer than the bromine-bromine because iodine is a larger atom, so has a longer bond length and hence a lower bond strength. So on page 3 of your notes, we're going to look at some dot-cross diagrams again. This time I'm showing them as two overlapping circles with the shared pair of electrons between them. So now each chlorine atom has got a complete outer shell. It's isoelectronic with a noble gas. So I'm going to do a few examples. So we're going to start with water, which has an oxygen and two hydrogens, H and H and an O. So they've got a covalent bond between the oxygen and the hydrogen. Again, notice I only show outer shell electrons when I'm doing these dot-cross diagrams. But oxygen has another 4 electrons in its outer shell, and I'm going to show those as two pairs. When I come to draw this in what we call a stick model, I have my oxygen and a single line representing a single covalent bond between the oxygens and the hydrogens. And we're also going to show the lone pairs on the oxygen there. Those lone pairs are very important and have a degree of impact on their chemistry. Let's look at ammonia. Again, we've got nitrogen this time. And this time I have 1, 2, 3 hydrogens. Again, each of those hydrogens is going to form a covalent bond with the nitrogen. But nitrogen has 2 electrons left over, so I'm just going to put the 2 electrons there as a lone pair. And again, if I draw the stick model of this, I get hydrogens. Notice this isn't 3D. We'll do 3D modelling when we do shapes later on in the year. And the last 2 on that page, I've drawn hydrogen chloride and I've drawn methane. Again, I can show it as a line, where each line represents a single covalent bond. And the last example at the top of page 4. So we've just drawn an ethane molecule. So notice again the single lines representing the single covalent bonds. I can not only have single bonds, I can also have double covalent bonds, in which I have 2 pairs of electrons which are shared between the donor atoms. So the first example I have is carbon dioxide. So I have 1 carbon and 2 oxygens. Each oxygen makes a double bond in this case. So I have a dot and a cross and a dot and a cross and a dot and a cross and a dot and a cross on that side. So that's my double bonds there. That uses up all of the carbon's electrons. Oxygen still has its 2 lone pairs of electrons. And again, if I draw it in stick model, I get this as my diagram, with 2 lines representing my double bonds. We can have oxygen, which again has a double bond between each of the oxygen atoms to make an oxygen molecule. Although I'm showing these as dots on one and crosses on another, we should remember that all the electrons are the same. And our last example is just going to be ethene with a double bond between the two carbons. And last in this section, we can also have a triple bond with 3 pairs of electrons. Nitrogen is one of the most common examples you're going to get of this triple bond, where I have 3 pairs of electrons shared between my nitrogen atoms. Again, they still have 1 lone pair each. So I've got nitrogen, 1, 2, 3, and another nitrogen. I suppose those should be crosses rather than dots, but it doesn't really matter. This triple bond of nitrogen makes it particularly strong. It's one of the reasons why nitrogen gas is so unreactive. And our last example here, C2H2, we have the carbon with a triple bond between it and another carbon, and then 2 hydrogens. So there's one special type of covalent bond that you need to be aware of, and that is a dative covalent bond. Now, if we consider an ammonia picking up a hydrogen ion to become an ammonium ion, we think about the dot cross in this case. We have a nitrogen, we have our 3 hydrogens all covalently bonded, so dot and cross on each of those, and we have the lone pair there. A hydrogen positive ion, on the other hand, has no electrons because it only had 1 to start with and it's lost 1. Now, a dative covalent bond basically is going to use this lone pair here to make a covalent bond with this hydrogen. So rather than 1 electron coming from each donor atom, 2 electrons come from 1 donor atom. And we draw them like this with a little arrow representing the dative covalent bond. So again, drawing it out in dot cross diagram, got some space, we've got the same nitrogen structure, my hydrogens, but this time the lone pair, which I'm going to show as 2 dots, has formed a bond with the hydrogen there at the top, giving the whole thing a positive charge. So that lone pair of electrons has been donated into the hydrogen's empty orbital. So 2 things you need for a dative covalent bond. You need that pair of electrons which is able to be donated, and you need somewhere for them to be donated to, in other words a vacant orbital or an electron deficient atom. Electron deficient simply means it's not got a complete outer shell, and it makes it much more stable, is this configuration. Now, the other thing to remember here is once you've actually formed this dative covalent bond, it is identical to a normal covalent bond. You can't tell the difference between the 2 of them. So I don't know actually, looking at it, which one of these hydrogens is forming the dative covalent bond. So another example is aluminium chloride, AlCl3. Aluminium, or at least anhydrous aluminium chloride, is a covalently bonded molecule. Aluminium here has a vacant orbital. The chlorines have lots of lone pairs. So 1 chlorine lone pair can donate into that empty orbital on the aluminium. And we get this structure, we sometimes call it a dimer, where we've got 2 molecules joined together. So our last example in this case is carbon monoxide. So carbon here has 4 electrons in its outer shell, oxygen has 6 electrons in its outer shell. Now I can make a double bond between the carbon and the oxygen, but if it tries to make a triple bond, that will push the numbers of electrons in oxygen's outer shell over 8. Now there's nothing wrong with that for a period 3 element, and we're going to have a look at that later. But for period 2 elements, we are limited to 8 electrons in their outer shell. So oxygen can't have more than 8 electrons in its outer shell. So the only way to accommodate and make sure that we've completed the electron shells in both carbon and oxygen is to have this dative covalent bond. So you have a carbon, double bond to the oxygen, but then you have a dative covalent bond. In this last section, we're going to look at atoms with expanded octets. So atoms in period 3 and beyond have what we call available d orbitals. Because if you think back to the electron structure, in the third principal quantum shell, we have a 3s, a 3p, and a 3d. And that 3d is available to us. And it means that we can put electrons into the 3d to go beyond 8 electrons in the outer shell. There's nothing sort of magic about 8. The only reason that period 2 elements can't do this is because in period 2 there is only 2s and 2p subshells. There are no 2d, so there's nowhere for that extra electrons to go. So our first example here is SF6, where the sulfur has bonded 6 times to the fluorine atoms. This is what we call an octahedral shape, and we'll study that a little bit later. But you can see there it's got 12 electrons in its outer shell. Our next example is PCl5, and here the phosphorus has 10 electrons in its outer shell, all of the chlorines making a single covalent bond. Last but not least, we have SO2, where the sulfur is forming a double bond to each of the oxygen, leaving 2 electrons in sulfur's outer shell, making a total of 10 electrons in the outer shell of sulfur. So we're just going to finish this section off by looking at some of the more difficult dot cross diagrams. So here we're going to look at an NO3 negative ion. So the negative means that one of the species in here which has gained an electron. So you can see here the star there representing the gained electron on the oxygen. Now that means that the oxygen only forms a single bond with the nitrogen, because if it formed a double bond it would push it over the limit of 8 electrons. Both oxygen and nitrogen are period 2 elements, so they can't expand their octet. They're limited to 8 electrons in their outer shell. So we're going to use dots to represent my oxygen. So we're basically going to have a single bond between that and my nitrogen, and then the normal dots representing my lone pairs. But because it's got that extra electron, it only needs to form one bond. Another one of these oxygens is just going to form the normal double bond that oxygen would normally form again, leaving my 2 lone pairs. Now the last one is a little bit tricky. I've now got 1, 2, 3, 4, 5, 6 electrons in its nitrogen's outer shell. If I was to make another double bond here, that would push it over the limit of 8. So I can't do another double bond to this oxygen. But I do have 2 electrons left on nitrogen. So I can use both of them to form a dative covalent, sorry that should be crosses, with the oxygen. So I have a single bond, a double bond, and a dative covalent bond. So if you think about what this would look like, a single bond to the oxygen, double bond to another oxygen, and a dative covalent bond to the third. And this one is overall a negative charge. The last example on this page is the dichromate ion, Cr2O72-. We need to read this very carefully. It's got a 2 negative charge. Now it's unlikely that both of those negatives are going to go onto the same atom. They're likely to go on 2 different atoms at 2 different parts of the molecule, or molecular ion in this case. So I'm going to put one here on this oxygen and one here on this oxygen. Now just as before, these oxygens will form a single covalent bond to the chromium, and they've still got their 2 lone pairs of electrons, and they've got a single electron which they've gained from somewhere else. The ordinary oxygens are going to just do the normal double bonds that they always do, so a dot and a cross and a dot and a cross with the lone pairs, and a dot and a cross and a dot and a cross, and the lone pairs, and the same with these bottom ones, dot and cross and dot and cross, cross and dot, it doesn't really matter. Sorry, cross and dot, cross and dot, and then I've got dot, dot to show the lone pairs. This oxygen in the middle is linking the two sides together, so it's forming a dot cross with one chromium and a dot cross with the other chromium, just like it does with water. So if we think about the stick diagram for this, you've got chromium double bonded to two oxygens, single bond to the oxygen with the negative charge on it. We've got our linking oxygen through to the other side, double bonds, double bond, single bond with a negative charge. Sometimes it's easier to kind of draw the line diagram first and then turn it into a dot cross diagram.